Hello Noddies, in our previous video, we designed a common source amplifier and simply applied a DC source to bias the gate. But wait, in a real chip, where does this DC source come from? Do analog designers simply place a battery inside the IC? Definitely not. So if you haven't watched that previous video, I highly recommend to watch that previous video by clicking the I button on the right top corner. So in today's video, let's learn how we actually bias a common source amplifier. In our previous video, our input was VGS is equal to V sin plus V bias and everything looked fine. But now imagine a real-time application. Maybe the input is coming from a microphone, or maybe it is coming from an antenna, or maybe it's coming from another amplifier stage. These source provide only the AC signal and the DC component is zero there, and they don't provide the DC bias that our transistor need. So the missing piece in our previous video was the bias circuit. Now let's try to design the bias circuit. So this is the method 1. The method 1 is external bias with the coupling capacitor. The simplest method is to use a external DC source and couple the AC signal through the capacitor. This capacitor blocks DC and allows only the AC signal. Here why do we need this capacitor? Because with the help of RG, it forms a high pass filter. Here the cutoff frequency is given by this formula. By selecting the proper capacitor value, we can control the lower cutoff frequency of the amplifier. Now how do we generally choose an RG? Here, generally we choose the resistor to be large because it gives us the high input impedance and it consumes very less power. Remember, I is equal to V by R. So large resistor means less current means less power required. Here, let's design for a cutoff frequency of 10 kHz. Here we are choosing the RG to be 500 kilo ohm and substituting this value in this formula, we get the capacitance to be 31.8 picofarad. Now let's try to simulate it in Cadence. And in our previous video, here we gave the DC voltage to be 433 millivolt. But we don't need this in the circuit because we are biasing it externally. So let me just give the DC voltage as 0 here. Only the amplitude is given as 20 millivolt and the frequency is set to 1 kilohertz. And here the AC magnitude is set as 1 volt for the AC analysis. Click OK, check and save, launch, ADL, choose your analysis as AC analysis. Here give you a start frequency as 1 and stop frequency as 10 MHz. Click OK, run your simulation, result, direct plot, ACDB20, click your output node and press escape in your keyboard. Here from this you can see there is no gain before the 10 kHz frequency and only the frequency above 10 kHz is passed. So our calculation is correct here. But there is still a drawback here. We still need an external DC source which is usually impractical inside an IC. So we go for the next method. In order to avoid an external bias source, we can generate the gate voltage using this 2 resistor. This is called as the voltage divider bias. Here the gate voltage is given by this formula and now the transistor can bias itself directly from the power supply. Here the coupling capacitor and the parallel combination of the resistor R1 and R2 again creates an high pass filter. And it also doesn't need an external DC source. So now let's try to design one. Here let us design for a cutoff frequency of 10 kHz for the VG of 433 millivolt and here I am fixing the VDD to be 1.2 volt and the R2 to be 100 kilo ohms. Substituting this value in this formula, I get the R1 as 177 kilo ohm and by substituting the R1 and R2 in the cutoff frequency formula, we get the capacitance to be 250 picofarad. Now let's try to simulate it in Cadence. Here I have rearranged the circuit, keeping the same AC analysis. Just run your simulation. After your simulation is complete, go to result, direct plot, ACDB20 and click your output node and press escape in your keyboard. So from this we can see there is a cutoff frequency of 10 kHz from this graph and the gain of 10 dB remains same here. This method is simple and widely used in discrete circuits, but in ICs it has a problem. Here we are using too much resistors. Here the resistor is very large and it consumes a lot of chip area. So in order to overcome this, we go for next method, the current mirror bias. We also have video for this current mirror. Press the I button to know more about the current mirror. Here, instead of using huge resistor, we use another transistor. This transistor is biased using a current mirror and automatically generate the required gate voltage. This approach has several advantages. No large resistor, less chip area, bias current can be tuned by changing the reference current, easy to adjust even after fabrication by controlling the bias current. And as usual, this circuit has its own trade-off. Designing an accurate constant current source itself is not easy, which is exactly why we spent several videos learning current mirror and current source before reaching to this point. So now let's try to simulate it in Cadence. Here I have rearranged the circuit. Here I have copied the same W by L for these two transistors. And all the other components are set the same. Now click check and save. Here go to aerial window and run your simulation. Result direct plot ACDB20. Click your output node and press escape in your keyboard. Here from this you can see the gain is the same. We have the 10 dB gain. And since there is no capacitor or resistor involved here, there is no high pass filter component here. Here since I have fixed the IDC to be 600 microamps, I have just kept the W by L same. You can just reduce the current by half, 300 microamps, and reduce the transistor width to be half, which is 4.65 micro. Check and save, and you can rerun your simulation. Go to ADL window, result, direct plot, ACDB20, click your output node, and press escape in your keyboard. Here from this graph you can see the gain remains the same, because as we know in current mirror, by doubling the W by L ratio of the copy current node, we can get 2 times of the reference current on the copy current. So here I have applied the same principle. Now since we have studied about the input side, now let's go to the output side. We know that the gain is given by minus Gm times Rd, and if we want a large gain, we need a large resistor. But in IC, resistor occupies area. Remember, R is equal to rho L by A, and for IC resistor, this is the formula, where R SH is the sheet resistance. In this example, I used a poly resistor, but resistor inside IC can also be implemented using diffusion resistor, well resistor, metal resistor, and high resistivity poly resistor. So different process provides different options. Here, for a poly sheet resistor, the resistance is said to be 100 ohms, and in order to design a RD of 1 kilo ohms, let's set the L by W ratio to be 10. So if the width is 0.5 micro, then we need a length of 5 micro, which approximately gives us an area of 2.5 micrometer square. Though it may seem small, as the gain requirement increase, the resistor becomes larger and larger. And a larger resistor brings more area, more parasitics, more process variation. So using a huge resistor as a load is not always practical. To overcome this problem, analog designers replace the resistor with active loads. In the next few videos, we will study several alternatives. NMOS in linear region, PMOS in linear region, NMOS diode connected load, PMOS diode connected load, and PMOS current mirror. These active loads allows us to achieve much higher gain while consuming much smaller area. And that's exactly where our common source amplifier journey continues. And that's all for today's video, Noddies. And as always, keep learning, keep simulating, and keep building.